The mathematics we learn in school doesn't quite do the field of mathematics justice. We only get a glimpse at one corner of it, but mathematics as a whole is a huge and wonderfully diverse subject. My aim with this video is to show you all of that amazing stuff. We'll start back at the very beginning. The origin of mathematics lies in counting. In fact, counting is not just a human trait, other animals are able to count as well. And evidence for human counting goes back to prehistoric times, with check marks made in bones. There were several innovations over the years, with the Egyptians having the first equation, the ancient Greeks making strides in many areas like geometry and numerology, and negative numbers were invented in China, and 0 as a number was first used in India. Then, in the golden age of Islam, Persian mathematicians made further strides and the first book on algebra was written. Then mathematics boomed in the Renaissance along with the sciences. Now there's a lot more to the history of mathematics than what I've just said, but I'm going to jump to the modern age and mathematics as we know it now. Modern mathematics can broadly be broken down into two areas. Pure maths, the study of mathematics for its own sake, and applied maths, when you develop mathematics to help solve some real-world problem. But there's a lot of crossover. In fact, many times in history, someone's gone off into the mathematical wilderness, motivated purely by curiosity and kind of guided by a sense of aesthetics. And then they've created a whole bunch of new mathematics, which is nice and interesting, but it doesn't really do anything useful. But then, say, 100 years later, someone will be working on some problem at the cutting edge of physics or computer science, and they'll discover that this old theory in pure math is exactly what they need to solve their real-world problems, which is amazing, I think. And this kind of thing has happened so many times over the last few centuries. It's interesting how often something so abstract ends up being really useful. But I should also mention that pure mathematics on its own is still a very valuable thing to do, because it can be fascinating and on its own can have a real beauty and elegance that almost becomes like art. Okay, enough of this highfalutin, let's get into it. Pure maths is made of several sections. The study of numbers starts with the natural numbers and what you can do with them with arithmetic operations. And then it looks at other kinds of numbers, like integers, which contain negative numbers, rational numbers, like fractions, real numbers, which include numbers like pi, which go off to infinite decimal points, and then complex numbers, and a whole bunch of others. Some numbers have interesting properties, like prime numbers, or pi, or the exponential. There are also properties of these number systems. For example, even though there's an infinite amount of both integers and real numbers, there are more real numbers than integers. So some infinities are bigger than others. The study of structures is where you start taking numbers and putting them into equations in the form of variables. Algebra contains the rules of how you then manipulate these equations. Here you'll also find vectors and matrices, which are multidimensional numbers, and the rules of how they relate to each other are captured in linear algebra. Number theory studies the features of everything in the last section on numbers, like the properties of prime numbers. Combinatorics looks at the properties of certain structures like trees, graphs, and other things that are made of discrete chunks that you can count. Group theory looks at objects that are related to each other in, well, groups. A familiar example is a Rubik's Cube, which is an example of a permutation group. And order theory investigates how to arrange objects following certain rules, like how something is a larger quantity than something else. The natural numbers are an example of an ordered set of objects, but anything with any two-way relationship can be ordered. Another part of pure mathematics looks at shapes and how they behave in spaces. The origin is in geometry, which includes Pythagoras, and is close to trigonometry, which I'm sure we're all familiar with from school. Also, there are fun things like fractal geometry, which are mathematical patterns which are scale invariant, which means you can zoom into them forever, and they always look kind of the same. Topology looks at different properties of spaces where you're allowed to continuously deform them but not tear or glue them. For example, a Mobius strip has only one surface and one edge, whatever you do to it. And coffee cups and donuts are the same thing, topologically speaking. Measure theory is a way to assign values to spaces or sets, tying together numbers and spaces. And finally, differential geometry looks at the properties of shapes on curved surfaces. For example, triangles have got different angles on a curved surface. And brings us to the next section, which is changes. The study of changes contains calculus, which involves integrals and differentials, which looks at the area spanned out by functions or the behaviour of gradients of functions. And vector calculus looks at the same thing but for vectors. Here we also find a bunch of other areas like dynamical systems, which looks at systems that evolve in time from one state to another, like fluid flows or things with feedback loops like ecosystems. And chaos theory, which studies dynamical systems that are very sensitive to initial conditions. Finally, complex analysis looks at the properties of functions with complex numbers. This brings us to applied mathematics. At this point, it's probably worth mentioning that everything here is a lot more interrelated than I've drawn. In reality, this map should look more like a web tying together all the different subjects, but you can only do so much on a two-dimensional plane, so I've laid them out as best I can. Okay, we'll start with physics, which uses just about everything on the left-hand side to some degree. Mathematical and theoretical physics has a very close relationship with pure maths. Mathematics is also used in the other natural sciences with mathematical chemistry and biomathematics, which look at loads of stuff from modelling molecules to evolutionary biology. Mathematics is also used extensively in engineering. Building things has taken a lot of maths since the Egyptians and Babylonian times. Very complex electrical systems like aeroplanes or the power grid use methods in dynamical systems called control theory. Numerical analysis is a mathematical tool commonly used in places where mathematics becomes too complex to solve completely. So instead you use lots of simple approximations and combine them all together to get a good approximate answers. For example, if you put a circle inside a square, throw darts at it, and then compare the number of darts in the circle and the square portions, you can approximate the value of pi. But in the real world, numerical analysis is done on huge computers. Game theory looks at what the best choices are given a set of rules and rational players, and it's used in economics when the players can be intelligent, but not always, and other areas like psychology and biology. Probability is the study of random events like coin tosses or dice or humans, and statistics is the study of large collections of random processes, or the organisation and analysis of data. This is obviously related to mathematical finance, where you want to model financial systems and get an edge to win all those fat stacks. Related to this is optimization, where you're trying to calculate the best choice amongst a set of many different options or constraints, which you normally visualize as trying to find the highest or lowest point of a function. Optimization problems are second nature to us humans, and we do them all the time, trying to get the best value for money or trying to maximize our happiness in some way. Another area that's very deeply related to pure mathematics is computer science, and the rules of computer science were actually derived in pure maths and is another example of something that was worked out way before programmable computers were built. Machine learning, the creation of intelligent computer systems, uses many areas in mathematics like linear algebra, optimization, dynamical systems, and probability. And finally, the theory of cryptography is very important to computation and uses a lot of pure maths like combinatorics and number